Welcome back to Math 124. Today we're going to be talking about the distribution of a proportion.
Let me remind you that we can use onlinestatbook.com to look at sampling distributions. As you can see, I have this set so that we're going to look at samples of 5 individuals from this bell-shaped distribution, and then we're going to take a look at samples of 25. So let's see if we can animate this. Viewing this web page through the lens of my editing software, the animation won't be quite as smooth as what we saw in class, but let's give it a try. Here we go, animated, taking 5, and there's the mean of that 5. Now it's choosing 25, and it will fill in the mean of those 25 individuals that it's sampled from the population, and that mean goes on the bottom. So let's do this 5 at a time for each of them. And there we go. That's after 5 samples of 5 individuals and 5 samples of 25 individuals. Let's do another 5 and another 5. And which one of these is approaching a bell-shaped distribution more quickly? Yes, the sample of 25 individuals has very quickly become bell-shaped. It's a very skinny bell, tall and skinny, but it became bell-shaped more quickly. You can see this even more if we don't begin with a bell-shaped distribution, but if we start with a strange-looking distribution like this one, and we take samples once again of 5 or of 25, 5 samples of each gives us these sampling distributions in lines 3 and 4. Another 5, another 5, another 5. Already these samples of 25 are looking more bell-shaped. And as we continue, it just becomes more so. It's going to take those samples of 5 a long time to get rid of all of the extra spikes. You see it a little bit still in the samples of 25, but not to this same extent. It's moving much more closely to a bell-shaped distribution. And as you can see, if you look over on the left, the standard deviation of the samples of 25 is less than the standard deviation of the samples of 5. Okay, so I think we're done with this for now. Let's move on. There is a theorem that describes what we have just seen as we've been generating distributions. It is called the central limit theorem. For random samples with a sufficiently large sample size, the distribution of many common sample statistics can be approximated with a normal distribution. Now, we have not been using this term normal distribution very much, but, well, perhaps we should talk just a little bit right now about what a normal distribution is. Here you can see some examples of normal distributions. Here there are more than one normal distribution plotted on each graph. And a normal distribution follows that bell-shaped curve. So instead of describing distributions as bell-shaped, we could describe them as approximately normal.
We use 2 important numbers to describe normal distributions.
One of them being the mean. As you can see, for this darker distribution here, the mean is at 0. Whereas for the gray distribution, the mean here is at 2. And this is one way to report the mean. And what would this be? This is the standard deviation. As you can see, the standard deviation of both the black curve and the gray curve in example A have different means but the same distribution. So their shape is roughly the same. The gray one is just shifted 2 to the right for the mean. In B, all of those distributions are centered on 0. 0 is the mean, but they all have different standard deviations. The tallest one has a standard deviation of 0.5 because within that distribution there, within one standard deviation above and below the mean, or minus 0.5 and plus 0.5 is 68% of the data, and 2 standard deviations above and below the mean would be here and here for the, once again, for the tall distribution here. That would contain 95% of the data. For our standard normal distribution, which has a mean of 0 and a standard deviation of 1. This is the standard normal distribution, the usual one we work with. Between 2 standard deviations above and below the mean is 95% of the data. That's the truth that we have been working with as we've been working with StatKey for the last few days. And then we have this distribution, which does have a mean of 0, but its standard deviation is 2. So you have to go all the way out to 4 above and below the mean to capture 95% of its data. As you can see, the data is more spread out. It has more variation. This tall, skinny one here with a mean of 0 and a standard deviation of 0.5, most of the data is really tightly clustered around 0. Let's take a closer look at one of these pictures, and I'm going to modify it a bit. And while we have this normal distribution here, and I already told you that this illustrates a mean of 2, so I could write mean here and standard deviation here. So if this were just a distribution of sample data, you took a sample, here's the data, here is how it is distributed, we would be talking about a mean, and we would be using this notation for it. And our standard deviation notation would be S, a regular S like we use every day in English. Now, if this were population data, we had all the data for a given population, for instance, all of the ages of you who are taking this class right now, the mean of your ages would be mu, and the standard deviation that we could calculate would be described as, or signified by, sigma.
Let's talk about what happens if we take samples of a certain size.
Say the size that we have said we need at least to do this reasonably. Take samples of size 30, and I take a sample, and you take a sample, and your classmate takes a sample, and we take lots of samples and get a sampling distribution. Well, it happens to be that the proportion of people in the U.S. who have brown eyes is 41%, or 0.41 is the population proportion. And if we take samples again and again and again, the mean of those sample proportions will be 0.41. And then instead of standard deviation, we will refer to the distance illustrated here as the standard error. Okay, nothing different than anything we've done before, except that now I'm going to tell you how to calculate that by hand and not rely on StatKey. The standard error of a sampling distribution for a population proportion will be P times 1 minus P over N. So in this case, for our samples of size N equals 30, this would be the square root of our P value is 0. This is not a P value. Our proportion is 0.41. Do not make that mistake. Times 1 minus 0.41 divided by N, which is 30. We will get a standard error of 0.090. That would be the standard error of our sampling distribution. The formula SE, or standard error, equals the square root of the population proportion times the quantity 1 minus p divided by the number in the sample is the formula for the distribution of a sample proportion if and only if these are true. The number in the sample times the population proportion must be greater than or equal to 10, and also the number in the sample times 1 minus the population proportion must be greater than or equal to 10, or you cannot use this formula. Well, why not? If you have a sample of 10 and you're taking samples of 10 repeatedly, when the population proportion of whatever you're measuring is only 5% or 0.05, the distribution of your sample proportion will look like this, which isn't really normal, right? So let's check what we're supposed to be checking. In order to use the standard error formula that I gave you, we have to have n times p greater than or equal to 10, and we must also have n times 1 minus p greater than or equal to 10. Oh, by the way, what is 1 minus p? Well, 1 minus p in this instance is 0.95. So let's see what each of those comes out to be. 10 is n, and p is 0.05.
And that equals
0.5, which is not greater than or equal to 10. Let's just check the other one just to see what happens. 10 times 0.95 gives 9.5, and that also is not greater than or equal to 10. So because I gave you these rules for using that standard error, you really don't need to know what this distribution looks like. You just have to trust me and generations of stats teachers that you can't use this formula here.
What would happen if we had the same proportion, but we took a larger sample?
Say 200. 1 minus p would equal 0.95. We just need to check both instances. Let's see. N times p, is that greater than or equal to 10? Well, n is 200, p is still 0.05, and that equals
10 exactly.
And 200 times 0.95, even bigger, 190. So is 10 greater than or equal to 10? Oh yeah. Is 190 greater than or equal to 10? Yes. And what does that distribution look like? It is approximately normal, even though my drawing is a little bit off. Remember that p here is our population proportion. In the case we were looking at most recently, that's the proportion of people who have brown eyes. And so 1 minus p would be the proportion of people who do not have brown eyes. So what this is saying is pick a sample size that's big enough that you'll have at least 10 or more people who have brown eyes, and you'll make sure your sample is big enough that you'll have at least 10 people who do not have brown eyes.
Here's the distribution again.
In this case, n equals 30, p equals 0.41, so n times p equals 12.3, which is greater than or equal to 10. Oh yeah, it is. And then we have 1 minus p, which is equal to 0.69, so that 30 times 0.69 equals 20.7, which once again is greater than 10. So we can accept that our standard error for this sampling distribution is 0.09.
And now that we understand where a sampling error comes from when we are dealing with the population proportion,
and we know how to calculate it, we can move on to calculating confidence intervals, which is what the next video will cover.